Hi everyone, I am Dr.A.RAKINI, Assistant Professor of Chemistry, A.D.M. College for Women, Autonomous, Nagapattinam. Now I am going to present my topic on Phenols. This topic present in 2nd BSc Chemistry, Major, Unit 5. Okay, let us see that introduction. In organic chemistry, phenol, sometimes called phenolics, are a class of chemical compounds containing of one or more hydroxyl group. It is like OH group bonded directly to an aromatic hydrocarbon group. The simplest is phenol, the formula of C6H5OH. This is structure of phenols, the benzene ring attached to OH group. Okay, the phenolic compounds are classified as simple phenols or polyphenols based on the number of phenol units in the molecules. Phenols are both synthesized industrially and produced by plants and microorganisms. Next one, properties. Phenols are more acidic than typical alcohols. The acidity of the hydroxyl group in phenol is commonly intermediate between that of aliphatic alcohols and carboxylic acids. The pK is usually between 10 and 12. The protonation of the phenols forms a corresponding negative phenolate ion or phenoxide ion, and the corresponding solids are called phenolates and phenoxides. Next one, condensation with aldehyde and ketones. Phenols are open to electrophilic aromatic substituents, and then the condensation with formaldehyde gives resinous materials, famously bakelite. This is structure of the another industrial scale electrophilic aromatic substitution is the production of bisphenol A, which is produced by the condensation with acetone. C, alkylation with alkanes. C means carbon alkylation with alkanes. Phenols is readily alkylated at the ortho positions using alkanes in the presence of Lewis acids such as aluminium phenoxides. This is structure. More than 1 lakh tons of tertiary butyl phenols are produced annually year 2000. In this way, using isobutylene as an alkylating agent, especially important is 2,6-ditertiary butyl phenol, versatile in the antioxidant. Next one, esterification. Phenols undergo esterification. Phenol ester or active ester being open to hydrolysis. Phenols are reactive species towards oxidation. The structure of oxidation, the oxidation cleavage, for instance, the cleavage of 1,2-dihydroxybenzene to the monomethylene ester of 2,4-hexadiene dienones acids, the oxygen copper chloride in pyridine. The oxidative dearomatization to quinones, also known as Tuber reaction, and oxones. The reaction depicted at the below 2,4,5-methylene phenol reacts with the singlet oxygen. The generation from the oxone sodium carbonate in an oxidates the water mixer to a para-peroxyquinone. This is hydroperoxide is reduced to the quinol with the sodium thiosulfate. And the next one, nomenclature of phenol. This is a very important one, nomenclature of phenols. Many phenolic compounds were discovered and used long before chemists were able to determine their structure. Therefore, tribal names, example, catechol, it is the IUPAC name of 1,2-benzene-diol. Next one, rasacinol, this is IUPAC name of 1,3-benzodiol. And then hydroquinone, this is one IUPAC name of 1,4-benzoquinol. Okay, they are often used to the most common phenolic compounds. In the systematic names are the more useful. However, because a systematic names specific the actual structure of the compound, if the hydroxyl group is the principal, the functional group of a phenol, the compound can be named as the substituted phenols, which carbon atom when pairing the hydroxyl group. For example, the systematic name for the thiamyl 5-methylene 2-isopropylene phenol. Phenols with only one other substituent can be named using either the numbers of the ortho 1,2, meta 1,4 and para 1,4 systems. The compounds with the other principal functional groups can be named with the hydroxyl group as a hydroxy substituent. For example, the systematic name for 2,4,6-triphenol, this is also called picric acid. The 2,4,6-trinitrophenol is also called picric acid. The 2-bromophenol is called orthobromophenol. 4-hydroxybenzoic acid is called para-hydrobenzoic acid. Next one, physical properties of phenols. Similar to alcohols, phenols have hydroxyl group that can participate in the intermolecular hydrogen bonding. In fact, phenols tend to form stronger hydrogen bonds than alcohols. See, chemical bonding, intermolecular forces. For more information about hydrogen bonding, hydrogen bonding results in the higher molecular bonds and much higher boiling point for phenols than for hydrocarbon with a similar molecular weight. For example, phenol molecular weight 94, boiling point 182 degrees Celsius, has a boiling point more than 70 degrees higher than that of toluene. The formula C6H5CH3. Then this is a molecular weight 92, boiling point 111 degrees Celsius. The ability of phenols to form strong hydrogen bonds also enhance the stability in water. Phenol dissolved to give a 9.3% solution in water compared with a 3.6% solution for cyclohexanol in water. The association between water and phenol is usually strong when crystalline phenol is left out in the wet environment. This picks up enough water from the air to form the liquid droplets. Next one, synthesis of phenol. The method of Cumin method. The most of phenol used today is produced from benzene through either hydrolysis of chlorobenzene or oxidation of isopropyl benzene. It is called cumin. The structure of cumin: oxidized cumin hydroperoxide after hydrolysis to give the phenols and then acetone. Next one, hydrolysis of chlorobenzene. This method although the Tau process. The benzene is easily converted to chlorobenzene by a variety of methods. One of which is the Tau process. Chlorobenzene is hydrolyzed by the strong base at a high temperature to give a phenoxide salt, which is acidified to phenol. Next one, oxidation of isopropyl benzene. Benzene is converted to isopropyl benzene. It is a fume by the treatment with the propylene and an acetic catalyst. The oxidation yield a hydroperoxide, cumin hydroperoxide, which undergoes acid catalyst rearrangement to phenol and acetone. Although this process seems more complicated than the Tau process, it is advantageous because it produces two valuable industrial products like phenol and acetone. General synthesis of phenol. To make more complicated phenolic compounds, a more general synthesis is needed. The cumin hydroperoxide reaction is fairly specific to phenol itself. The Tau process is somewhat more general, but the conditions required often led to a low yield, and the mere destroyed and the other functional groups on the molecule. A milder, more general reaction is the diazotization of the arylamine, a derivative of a aniline, the formula C6H5NH2, to give a diazonium salt, which hydrolyzes to a phenol. Most functional groups can survive these techniques as long as they are stable in the presence of dilute acid. Next one, different properties of phenols. Although the phenols are often considered simply as aromatic alcohols, they do have somewhat different properties. The most recognized difference in the increased acidity of phenols. Phenols are not as acidic as carboxylic acid, but they are much more acidic than aliphatic alcohols, and they are more acidic than water. Unlike simple alcohols, most phenols are completely deprotonated by the sodium hydroxide. Next one, quinones. This is one important topic. It's a quinones. Like other alcohols, phenols undergo oxidation, but they give different types of products from those seen with the aliphatic alcohol. For example, chromic acid oxidized most phenols to conjugated 1,4-diketones called quinones. In the presence of oxygen in the air, many phenols slowly oxidized to give dark mixings of containing quinones. Next, hydroquinones. Hydroquinone, there is a IUPAC name of 1,4-benzene-thiol. 1,4-benzene-thiol is a particularly easy compound to oxidize because it has two hydroxyl group in the proper relationship to give up the hydrogen atom to form a quinones. Hydroquinones is used in developing photographic film fiber, reducing activated exposed to light. Silver bromide, in example, silver bromide to black metallic silver, AG. Unexposed grains of silver bromide react more slowly than the exposed grains. Next one, electrophilic aromatic substitution. Phenols are highly reactive towards electrophilic aromatic substitution because the non-bonding electrons on oxygen stabilize the intermediate cation. This stabilization is mostly effective for attack at the ortho or para position of the ring. Therefore, the hydroxyl group of a phenol is considered to be activating. Example, it is here presence causes the aromatic ring to the more reactive than the benzene or ortho and para directing. Next one, picric acid. This is structure of picric acid. So other name of 2,4,6-dinitrophenol from phenol is the important explosive that was used to World War I. On effective explosive of needs to high the proportion of the oxidation groups such as nitro groups. Nitro groups are a strongly deactivating. Example, make the aromatic ring less reactive. However, and it is often difficult to add a second or third nitro group to an aromatic compound. 3 nitro groups are more easily substituted on the phenol because the strong oxidation of the hydroxyl groups help to consider to the deactivation of the first and second nitro groups. Next one, salicylic acid. This reaction is used commercially to make salicylic acid from conversion to aspirin and methyl salicylate. This is structure of salicylic produced structure, and the phenoxide ions generated by the treating a phenol with sodium hydroxide are so strongly activated that they undergo electrophilic aromatic substitution even with the very weak electrophile such as carbon dioxide. Phenol interact with the active metal. Okay, acidity of phenol. When phenols interact with active metals like potassium, sodium, etc., the corresponding phenoxide is formed. These phenolic reactions show that is an acidic substance. The hydroxyl group is phenol is directly connected to sp2 hybridized carbon of the benzene ring, which functions as a electron withdrawing groups. As a result, the electron density on oxygen is reduced. The phenoxide ion creates stability compared to alkoxide ions because of the delocalization of negative charge within the benzene ring. Phenols are therefore more acidic than the alcohols. When it comes to the substituent in the phenols, an electron donating group attached to the ring results in the decreases in acidity, versus an electron withdrawing group results in an increases in acidity. Next one, chemical properties of phenols. The electrophilic substitution reaction on electrophile can more easily attack the benzene ring due to the increased electron density caused by the presence of an hydroxyl group on it. When the benzene ring is involved in electrophilic substitution reactions, the ortho and para carbon of benzene have more electrons than the meta position due to the presence of an hydroxyl group, OH group, and the term ortho and para directing group refer to the OH group. The reactions of phenol involving the cleavage of OH bond. The first one reaction of Holt's reaction. The phenols produced sodium salicylate through a reaction with sodium hydroxide and carbon dioxide, which then acidifies to produce salicylic acid. When an aromatic electrophilic substitution, the phenoxide particles formed with sodium hydroxide is more reactive than phenol, and it is thus acidific to provide hydroxyl acids. Next one reaction of Reamer-Teamer reactions. When phenol reacts with chloroform CHCl3 in the presence of sodium hydroxide NaOH, an aryl aldehyde is produced. A group known as aldehyde is CHO is a aldehyde. This is bought in the ring. This is a process is referred as the Reamer-Teamer reactions. Dichlorocarbene is the name given to the electrophile from the form this reaction CCl2. The salicylic aldehyde, the end product is produced by the hydrolysis intermediate substituent the benzyl chloride in the presence of alkali. Next one, phase rearrangement. When phenol ester are arranged in the presence of anhydrous aluminium trichloride AlCl3 is aluminium trichloride, the phenol ketones are produced. The phase rearrangement is the term for these reactions. Next one, acetylation. The acetylation is a process by which phenols react with an acid anhydride and introduced the acetyl radical. Acetyl radical is CH3CO. Aspirin in the resultant the substance. Next one is nitration. Nitration is the addition of NO2 group into the ring at 298 Kelvin. At a low temperature, phenol combines with dilute acid to produce ortho and para nitrophenols. And the steam distillation is the frequently used to separate the ortho and para nitrophenols that are produced, versus para nitrophenol has less volatility to the intermolecular hydrogen bonding. Ortho nitrophenol is steam volatile to the intermolecular hydrogen bonding after being treated with the concentrated nitric acid. Phenols produced two trinitrophenols are acid. The yield is not very good. The next one, halogenation. The halogenation under different experimental conditions, phenols and bromine react to produce entirely different products. Monochromous phenols are produced when it is reacted with bromine in the low polarity solvent such as CH2 or chloroform at low temperatures. And the relation is the only the ring is positions 1 and 4 will be activated by the non-polar or low polar solvents. Therefore, only monosubstituted products are produced. Next, reaction with zinc test. When phenols reaction with zinc test. When phenol is distilled with the zinc dust, it gives benzene. This is an example of reduction. Next one, reaction with ammonia. And the reaction between phenols and ammonia, which occur in the presence of anhydrous zinc chloride, produce aniline. In the end, these reactions result in the release of water. Next one, carbolic acids. The phenols are organic compounds containing a benzene ring bonded to a hydroxyl group. They are also known as carbolic acids. The phenols react with the active metals like sodium and potassium to form phenoxide. These reactions phenols with the metals indicate its acidic nature. Phenols react with the aqueous sodium hydroxide to produce phenoxide ion. This is indicate that the acidity of phenols is higher in comparison to the alcohols and water molecules. Next one, the explanation for the acidity of phenols. The acidity of phenols is due to their ability to lose hydrogen ions to form phenoxide ion. In a phenol molecules, the sp2 hybridized carbon atom of the benzene ring attached directly to the hydroxyl group acts as an electron withdrawing group. This is sp2 hybridized carbon atom of a benzene ring attached directly to the hydroxyl group has higher electronegativity in comparison to the hydroxyl group. Due to the higher electronegativity of the carbon atom in the comparison to the hydroxyl group, attached. The electron density decreases on the oxygen atom. The decreases in electron density increases the polarity of oxygen hydrogen bond OH bond. The result in the increases of ionization of phenols. Thus, the phenoxide ion is formed to be phenoxide ions formed is stabilized by the delocalized of the negative charge due to the resonance in the benzene ring. The phenoxide ion is a greater stability the phenols as in the case of phenols. Charge separation takes place during this is called resonance. Next one, resonance structure. The resonance structure is phenoxide ion. We explain the delocalization of negative charge. In the case of substituted phenols, the acidity of phenols increases in the presence of the electron withdrawing group. This is to the stability of the phenoxide ion generated. The acidity of phenols further increases in the phenols are attached at ortho and para positions. This is to the fact that the negative charge in the phenoxide ion is mainly delocalized at the ortho and para position of the attached benzene ring. On the other hand, the acidity of phenols decreases in the presence of electron donating groups as they prohibit the formation of phenoxide ions. Next one, phenolphthalein. The reaction of phenols with phenolphthalein anhydride. When phenols is treated with phenolphthalic anhydride, it will lead to the formation of phenolphthalein. Phenolphthalein, when it is in non-acidic medium, remains the colorless, but it is a basic medium. Its color changes to pink. It is used as an indicator for the test of acidic and basic mediums. Next one, resorcinol. The resorcinol formula C6H6O2. What is resorcinol? The resorcinol is an organic compound with the chemical formula C6H6O2. It is one of the three isomeric benzodiols in the white and soluble in water. It is known as resorcin. The Indian meta-dihydroxybenzene. It is a 1,3 isomer for benzodiol. It is a benzene diol, that is a benzene dihydroxylated at positions number 3 and 1. It is positioned as a sensitivations and the erythrom and the Peitner inhibitor. The resorcin is a crystalline solid, very white and soluble in water, ether and alcohol. It has a odor with a sweetness to a bitter taste. It does not dissolve carbon disulfate and chloroform. It turns it pink when exposed to light. If it is not, it is a pure form. If pans, however, difficult to ignite. It is widely used in the making pharmaceutical and plastics. The resorcinol or 1,3-dihydroxybenzene can be obtained by the sulfonation of benzene. The benzene is susceptible to the electrophilic substitution reaction. The sulfur dioxide acts as the electrophile and generated the benzene disulfonic acid. The alkali fusion replaced the sulfonic groups by the hydroxyl group. In the sulfonation of benzene, the benzene is heated in the presence of fuming sulfuric acid, meaning H2SO4, and the sulfur trioxide SO3 to produce the benzene sulfonic acid. In excess of sulfonation reagents, the benzene is converted in the substituent derivative of a benzene. Here, sulfur trioxide is a neutral electrophile. This delocalized electron of the benzene attack on sulfur trioxide and generated the benzene sulfonic acids. Next one, last one, uses of resorcinol. The C6H6O2. The resorcinol is used as a disinfectant or an antiseptic in pharmaceutical products. It is used to treat skin infections such as acne. It is used in manufacturing of resins. It is an analytical reagent used to determine the quality of ketosis. Okay, students, I would like to ask you some questions and know the correct answers. Okay, question 1. What is the main use of phenol? Answer. Phenol is an antiseptic and disinfectant used in a variety of settings. Phenol is an antiseptic and disinfectant. It is a active agent, a wide range of microorganisms including some fungi and viruses but is only slowly effective agents. Phenol has been used to disinfect skin and relieve itching. The second one, what is the theory of phenol? Phenol is a commonly studied compound in organic chemistry that is formed by the addition of the hydroxy functional group to an aromatic ring. And the hydroxy functional group is formed by the covalent body between an oxygen and then hydrogen atom. Okay, third one, how to prepare phenols from cumin is an organic compound obtained by Friedel-Crafts alkylation of benzene with propylene. Okay, and upon the oxidation of cumin isopropyl benzenes in the presence of air, cum hydroperoxide is the, and upon the further treatment of cum hydroperoxide with the dilute acid, phenols are obtained. Okay, fourth one, how is phenol classified? Phenols are classified based on the number of hydroxyl groups they contain. Monohydric phenols, these phenols have one OH group. Next one, dihydroxyphenol, these contain two OH groups. There can be ortho and meta or para derivatives. Okay, that's it for today's session. Hope you will understand all the topics in the session. Okay, thank you.